recorded in the cloud. Don't want those files on my computer. They're big, and I forget to delete them because Zoom, like many Apple products, finds a way to hide the damn files in a place that, you know, who knows where. Anyway, last time we started talking in detail about file systems. The reason why it's important for you to understand file systems is because that's where the files are. And by understanding the way that files are file systems are constructed, can help you write code that runs faster. Okay, so if you're aware of how the file system is built, you can avoid practices which will slow you down. For example, if you know that the block size of a file system is 16 kilobytes, if you read, if you want to seek somewhere that's not on a 16 kilobyte boundary, or read from that, that might be slower than if you did all of your I/O on the same boundaries as the file system itself. So I'm going to start sharing my iPad, and I've come up with two things to do today. One is a software engineering question, and let me show you that. Okay. So look at the top here. And I've identified 3 steps to adding a block to a file. Let me see if I can now see everybody's faces or black boxes. Fine. Okay. So, and I want to order them in the optimal order of operations. The 3 steps that I identified are getting a free block, because certainly a file system, one of the jobs of the file system is to keep track of the blocks that are allocated versus the blocks that are unallocated. Now, what do we call the data structure that keeps track of the allocated blocks? You know the answer to this. Go ahead. If a block is allocated, what's it doing? Anybody?
It's being written onto the stack or into a directory.
Okay, I don't understand the first part, but the second part is in the right direction. Yeah, a block from the file system could be part of a directory. What else could it be part of?
I just misspoke in the first part.
That's okay. All right, so this is making me sad. If a file, if a block has been allocated, what was it allocated to? We got one answer so far. It might be allocated to directories.
Possibly a stupid answer, but memory.
It's well, you know what? Some blocks on a disk are associated with memory, but they live in their own location. And what I mean by that is modern operating systems support a swap space, which holds the contents of memory when it's not present, physically present in memory for on a temporary basis. But the swap space is not part of a file system. So Blake, your answer is kind of okay, but in the end of the day, not exactly right. All right. All right. So if a block is not allocated, what's it doing? Is it a free block? It's not allocated, it must be free, right? So if it is allocated, it must be all right, everybody, hold out your palms like this. Okay, now turn your palm around like this and hit yourselves. Okay, if it's an allocated block, it must be part of a file, right? Okay, now why couldn't anybody say file? So Noel was closest. He said directory, because directory is a file.
Don't highlight me. I don't want to be the teacher's pet.
Ah, you're not in danger of that, no. Okay, I'm kidding. All right, so coming back up to the top of the page here, that's where I jumped off on the notion of a free block. So actually, we didn't answer the question. So what is it that keeps track of allocated blocks?
It wouldn't be the inode table, would it?
Well, exactly. It would be exactly that. If a block is allocated, there exists at most one inode that contains think of it as a pointer to that file. I'm sorry, that block. I was doing two things at once. Let me get back. Okay. So what is it that keeps track of allocated blocks? Well, it's inodes. If a block is allocated, it must be part of a file or a directory, which is also files. And but however, so maybe it contains data, but if it doesn't contain data, what's another kind of use for an allocated block? We discussed it last time.
Metadata?
Well, the metadata about a file is held in the inode, right? But an inode contains a list of pointers to data blocks, the first 10 of which are data blocks themselves, but then the 11th, 12th, and 13th is weird. It's different. So if a block that's allocated to a file is not holding data, it must be an in die.
The indirect nodes?
Right, right. So there's two things that an allocated block can hold. One is data. The other is pointers to data. Because recall that in order to scale to large files, we have a hierarchical structure. Now, let's take an observation here. If you were doing a tree structure, maybe you would do it as a balanced tree so that there was only one tree. If it was balanced, that means that access to any leaf would be would be rapid. But what about what about why do we what Noah, did you have a question?
Well, yeah, if we're storing them in a tree, would a depth first or a breadth first search be preferable to find one of them?
Okay, well, that's an interesting question because uh, accessing blocks in the hierarchical organization of the of the pointers of the inode doesn't really involve searches at all, right? Because if you know that you want byte number n, there's an algorithm to compute which pointer is going to hold the nth byte. So there's never really a search.
Okay, so there's already a built-in algorithm with the hierarchical system in order to find whatever we need.
Yes. So for example, let's take a quick moment. I was going to do this kind of later, but we'll just come back to this later. So suppose the block size was n, and we're interested in byte b. Okay, so how do we find the block within the file that contains byte b? Well, if b is less than 10 times n, then the block number is equal to b divided by n. Okay, so where did that 10 come from? It was only on Monday.
Is it something to do with a pointer that's pointing to B?
It'll be a pointer that's pointing to the block holding byte number b. All right, so where did the 10 come from?
I remember you writing the math, but I do not remember the math.
I also drew a picture. Okay, I'm going to scroll up on my iPad a little bit. And there it is, right here. One, two, three, four, five, six, seven, 8, 9, 10 direct blocks. And
Okay, so mm, mm, uh, tell me if I'm reading this wrong, but so what you're saying is that we're checking whether the inode has 10 direct blocks or not?
no, not exactly. So Noah, you were interested in what that algorithm was. So I was just starting out the definition of the algorithm. So
Okay.
let's say n was 512. So 10 times 512 would be 5,120. So if B is less than 5,120, it must be pointed to by one of the direct block pointers. So if n, the block size, if the block size is 512, that means these 10 pointers have the capacity to keep track of 5,120 bytes. So if B is less than 5,120, it's going to be in one of these, referred to by one of these. Which one? B divided by 512. So byte number 7, B divided by 7 divided by 512 is 0. It's going to be pointed to by that block. If, let's say, B was 540, 540 divided by 512 is 1. It's going to be pointed to by that block, and so on. Okay? All right. Okay, so moving on. If B is less than 10 times n plus 128 times n. So notice the order of the if statements. This one comes first. So if it was less than 10 times n, it would be handled here. If it's more than 10 times n and less than 10 times n plus 128 times n, or let's write it down, 138 times n, then you fetch the single indirect block, then find which pointer in that block is the right one. And what is the math for that, please? Okay, so it would be B minus, what's come before it? Well, what's come before it is 10 times n divided by n. So let's try block number 5,121, byte number.
Well, I have a question. Why
Yeah.
do we not get rid of, because if we're doing the math backwards, why do we not get rid of, why do we not divide by 128 times n?
Divide by 128 times n.
Because the math up there is if b is less than 10 times n plus 128 times n. I don't know if I'm just misunderstanding something.
Yeah, well, if this is true, it means that the byte number we're looking for is held in one of the first 138 blocks. And we know that it's not in the first 10 blocks because if it were, it would have been handled here. So this means that the byte we're interested in is in a block which is between the 11th and the 138th, 137. Okay. All right, so if that's not true, well, yes, we're going to do the, it's a double indirect. So if B is less than 138 times n, which we got from here, plus 128 squared times n. Okay, then it's found via a double indirect. Okay, so and then so on for the triple indirect. Okay, take a look. So single, double, triple. Let's change this question into how many IOs does it take? Let's say if you just did an open and did a seek to a particular location in the file, maybe position B, how many IOs would it take to get that block? Well, if it's here, that's not what I wanted to do. I wanted to do this. If it's one of these, then it takes only one IO. That's why it's called direct. If it's found underneath here, it will be one IO to get the single indirect block, and then a second IO to get the data. If it's here, it's going to be one IO to get the double indirect block, followed by another IO to get the block that is pointed to by the root of the node. That second block is also an interior node. It will take a third IO to get to the data, and so on. So if it's underneath the triple indirect, it will be one IO to get the root, a second IO to get the mid-level, the third IO to get the bottom level of the interior nodes, and a fourth IO to get the data. Okay, if you want
And
to
is
draw
that
it.
the peak of how many we need?
Yes, so this file system structure maximum is 4 IOs to get one block of data. So the direct is a direct pointer to data. The single indirect is a pointer to a block, which contains a pointer to data. Double indirect contains a pointer to a block, which contains pointers to more blocks, which contain pointers to data. So now you can see it's called single indirect because you've got one layer in between. It's called double indirect because your tree now has 2 layers, and triple indirect now has 3 layers before you get to the leaves. Okay. Brandon, do you have a question?
Yeah, so when you were speaking about like it having 10 direct pointers, is that just a case for like the earlier versions of the extended file system? Because as far as I've seen, it's talking about 12 direct pointers, if that's only a case for ext4.
Right. So the newer file systems have slightly different structures. Now, another thing is that the original Unix file system encompassed the idea of a 512 byte block. Modern file systems today are anywhere, it's a user tunable parameter. So it's anywhere from 16 kilobytes to 64 kilobytes per block. Has anyone here ever formatted a disk under Windows or the Mac? one of your choices is how big the block size is. So if disk drives keep getting bigger, then the basic block size has to get bigger. Otherwise, we devote too much data to just keeping track of blocks. So when you want to keep track of the same number of blocks with less metadata, less pointers, well, you just make the blocks bigger.
But there's
Make
still an
sense?
option to make your blocks smaller than default size, I think, right? It's been very
Right.
long since I formatted anything.
Yes. So yeah, you still have the option of making a file system with a smaller block size, but given also today's usage patterns of bigger and bigger files, it means you're introducing a requirement of more overhead if you are using small block sizes. So, if you go out into the field and you become the person in charge of a data farm, you might want to do an analysis of file sizes. So if the most common file size is very small, well, your block size can be fairly small. But if your most common file size is very large, then you make your blocks very large. Okay. All right. All right. So here are these three things. Identify and how to get a free block. So there is something that keeps track of the free blocks. The data structure that keeps track of the allocated blocks are the inodes, which we painfully came to. The data structure which keeps track of the free blocks, we won't go into much detail. We'll just give it its name. It's called the free block list. Big surprise. Okay. So here's another step in writing a new block of data to a file. At some point, you've got to link that free block, that formally free block, to the file that you're adding to, right? Make sense? Okay, and then another step is you've actually got to put the data in the block. You got to write it out to disk. So here are three steps that you have to go through in order to add data to a file. What order should they come in?
I think it's identify the free block, write the data to block, then link it to the inode, or link it to the file.
All right, well, let's try that. Okay, good. And Noah, you think what comes next?
Yeah, identify, then write the data.
Then write the data.
Yeah, write the data to the block.
Okay, and then that would make this one number 3, correct?
Yeah.
Okay. Well, Noah, you are absolutely right, but that's not where file systems started. And I wrote them in this order as an attempt to trick you into thinking this was the correct order. But Noah, you actually identified the right correct order. But now let's look at the wrong correct order. All right, because anything that ends in a block being linked to a file properly and having data written to it, any order of steps is going to be correct. But some orders are going to be better than others. And that is the software engineering question that I wanted you to start thinking about in your future. Okay. So as you design bigger and bigger systems, You may have multiple paths which lead to a correct outcome, but some of those paths will increase the likelihood of data corruption, and other paths will decrease the likelihood of data corruption. So I'd like you to bear that in mind as you design bigger and bigger things when you leave Carthage. So let's imagine that Noah didn't give us the right answer, and let's look at the wrong right answer, which would be this. This is the order in which the original Unix file system did things. It would go get a block off the free list, so it would update the free list. It would add it to an inode, and then it would write the data.
But didn't you say that once you link a block to a file that's no longer free, are you still allowed to write data to a block that's not free?
Well, definitely. You can write
Okay.
to a block that is not free. Perhaps, well, you just can. If you were overwriting some part of your own data, you would be doing that because that block is already part of your file. And if you were adding new data to, let's say, the end of the file, the block is, as you identified correctly, Noah, the first step is to remove the block from the free list.
All right, thanks.
Okay. So what if you did it in this order? What's wrong with it?
If you were to link first, then write,
Yeah.
wouldn't that mean like as the question states, if the power is lost, since you link to it, those blocks are considered essentially owned, but technically they're not completely written to because the power went out. So you caused the chance of a data corruption then.
Right. That's exactly right. So what you should do in your futures is to play some hypothetical what if games to determine the order in which you'll do the least harm. So if what's the harm if the power goes out here? Okay, so here. Power goes out there. You've taken a block off the free list, and then the power goes out. Any harm done?
Those blocks, you can't get them the next time because now they're not free.
Okay, so the block is no longer on the free list, and it's not part of a file. So Eric is saying that the block is lost. Is that what you're saying, Eric?
Yeah, I think so.
Okay, well, temporarily, you're correct. It is lost. However, typically during rebooting, the file system is going to be checked. And think about it. We have perfect knowledge of what every block on the file system is supposed to be doing. So in the data area, if an inode points to a block, it's allocated. If the free list points to a block, it's free. But if it shows up in neither, oh, well, it's just one of these lost blocks. Let's just add it to the free list again. Okay, so temporarily it's lost. Okay, so if the power goes out here, no harm done. If the power goes out here, no harm done. The data has been persisted to the drive. But what if the power goes out here? Okay, I think somebody's already said it, that there is a block linked to a file which contains garbage. And there's no way to know that it's garbage because the inode's already been updated. Okay, so as it turned out, this, as I said, is the order of operations in the original Unix file system. And there was file system corruption all over the place. File systems would become routinely corrupted. They identified this bad choice, and simply by modifying this order of operations to be what Noah said originally, dramatically improve the reliability of the file system. I mean, literally, I mean, think about it. If it was just function calls, we just reordered 2 steps, 2 function calls. And we dramatically improve the reliability of the system. So this is a really good lesson in software engineering. Okay, anybody have any questions? Okay, so the next thing I want to do is go over, let's just say we remember this, and I'm going to erase it because I want more room. All right. I suppose there's a different way of erasing, is there? No, there isn't. Okay. That's good enough. All right. So what I'd like to do is go over, once again, you're looking at the original Unix file system. And I want to go over what kind of performance would you get just by opening a file, /foo, and seeking to byte 21,000. Okay. Okay, go away. All right. So let's talk about what's necessary. So if we are opening a file /foo, it means it's in the current directory. So let's assume the current directory is already loaded in RAM. Okay. So the directory is a table of names and numbers. This column, as you recall, are inode numbers. And this is names. Okay, so step 1 is search through all of the names that are found in the directory. If the directory is large enough, it will span multiple data blocks. So yes, you might have to do some IO in order to find the inode number of the file you're interested in this case, foo. But let's ignore that. So let's pick this up at the point in which we know the inode number of foo, /foo. Okay. All right. So now we're starting to count IOs. So IO number 1 is you've got to do a seek to somewhere in here in the inode array. And the purpose of that seek is to load the inode of foo. Okay. Then now you have the inode for foo in RAM. You figure out which pointer is responsible for pointing at byte number 21,000? Okay, so let's work that out. So that's one IO, and then some computation. So 21,000 minus 5,120. Somebody get out their calculator, do the math for me. Is going to be what?
15,880, I think. That's 51.
15,880.
Yeah, that's 5120 in the bottom right.
Good. Okay. So, and then divide this by 512. And what's that answer?
Uh, 31.02.
Okay, but it's integer division, so it's 31. So we'll go to the pointer number 31 and get a block number. So that means, so we've done one IO to get the inode. In fact, I even made it red so far already. And then we're going to do a second IO to get the appropriate data block. Okay, so let's say this was the appropriate data block. Okay. So far we've been doing seeks to here, to the inode area. Seeks take a long time. And then we seek to the data area. So you can see where I'm going with this, that we're going to spend and lose a lot of time seeking back and forth between the data area and the inode area. So the performance of this file system was very low. Pair that with the fact that disks were much slower in those days. So this was glacial. This was really slow. So can you think of a way, propose a way to speed up IO just by modifying this layout? So now I'm asking you to be an architect of the file system. Can you come up with an idea that would allow us to pretty much keep the same architecture, but it would be a lot faster?
Would it be beneficial to place the data blocks before the inodes in that hierarchical system? Or am I reading
Okay.
this wrong?
So, well, let me draw a picture and we'll talk about it. So right now we have this where you have inodes followed by data blocks. So you're just saying have data blocks followed by inodes. Is that correct? Okay.
That was my idea.
Well, I think maybe this would result in the same performance. Because the problem here is that we're always seeking back to here and then out to here, then back to here, then out to here. So that would be pretty much, I think, the same with this diagram. Okay, how about can we have another idea?
I may have just missed it, but why are you constantly seeking back and forth?
Well, because inodes are frequently accessed and data blocks are frequently accessed. And potentially, let's go back up to this picture. Potentially, the data block needed for in reference to a file pointed to by this inode might be all the way at the back here.
Can we kind of splice the data blocks and inodes together and place the inode next to the data block that it refers
Yes, that is the big change. So Connor, that's the perfect answer. I believe I understand you correctly. If so, it's the perfect answer. I'm pretty sure I understand you correctly. And that is the evolution of the fast file system. So we just studied the original Unix file system, and now here's the successor to it. So let's change the, yuck, that's a terrible horizontal line. It's slightly better. So we still have our super block here. And then we have some inodes and then some data blocks and then some more inodes and then some more data blocks and then some more inodes and then some more data blocks and so on. And then we add some smarts to the file system algorithm that says, if your inode is here, then arrange for the data blocks to be nearby, so that seeking is a much shorter distance. Okay? So why am I going over this in computer organization class? Well, it is organization of a file system, so there's that. But the real reason is I'm trying to get you to influence how you approach problem solving as you go out into the field. I mean, you're, after all, you're juniors and seniors, you're close to being done. So what I'm prompting you with are questions like, if there's a number of different orders that I can do a certain thing, which order does the least harm? Okay, or a question like, I need to store data, I need to store a certain set of data. Is there a layout that would increase performance? So it's not just thinking of the right data structure. Now I want you to think on a deeper level, which is very much computer or comp org appropriate. Like we study assembly language because I want you to think about what's under the hood. Okay, so now we're looking at much bigger data structures. And I want you to think about, again, what's under the hood. And in thinking about those questions and in answering those questions, you'll be superior engineers. Okay, anybody have any questions? Okay, so those were, I think, 2 good lessons for today. And that's all I have. So make sure you hand in your projects, and I'll see you on Friday.
Bye.
Thank you.
Bye.